So one of the most important tools we use to solve a set of nonlinear equations is the Newton-raphson procedure, and most of you would be familiar with the Newton-raphson procedure for a function of single variable. So f is a function, it's a nonlinear function, and it's a function of a single variable x. The way we solve it is through an iterative method, which means we start with a guess x0. From that guess, we generate a next better estimate x1, then go on to x2, and so on till we get a satisfactory solution to x, which makes fx equal to 0. Now, uh, since most of you are aware of this procedure and might have used it in different contexts, uh, let us assume that I have reached the kth guess. So now from kth guess, I want to generate the k plus 1th guess. And to do that, I expand the function fx about xk. So I do it for xk plus delta uk, where delta uk is a small increment in the value of x over xk. So this is my xk plus 1, which is slightly away from xk. I expand it in the Taylor series, and if I do that, then I get fxk plus df dx evaluated at xk times delta uk plus the second derivative delta uk square and so on. I truncate it at this point, so I neglect all these terms, and then I am left with fx k plus 1 equal to fxk, which is a value that I know because xk I have found earlier, times this quantity involving the first derivative, which for this 1D case can be written as the d of fxk in the direction of delta uk. In this case, this and this are actually the same expression, trivially the same expression. Now, now let us hope that xk plus 1 is a better estimate. So let us now set fxk plus 1 equal to 0, and if we do that, we have fxk plus d of fxk delta u, the k equal to 0, and uh, and we know that in this case this means that fxk plus uh, this d is df dx at xk times delta uk is equal to 0, which leads to the fact that delta uk, now we can solve for delta uk, is equal to minus fxk divided by df dx evaluated at xk. This is delta uk, which means that once we have solved for delta uk, we can now go back and construct our next best iteration, which is xk plus 1, and it's constructed as xk plus delta uk. We then go back to this step, keep repeating this till xk plus 1 and xk become, for all practical purposes, become equal to each other. That means that means delta uk starts becoming close to 0. So this is the Newton-raphson procedure for a 1D system, and this is the equation that you use. This is the equation that you use to generate the increment in the guess value. So if you know the kth guess value, then the increment in the kth guess value is generated through this equation. The way this works, you might already be aware of it. So this is my function. Let's say this is my function fx, and this is the point where fx is equal to 0. So I want to find this value of x. Let this be x star. X star is the value of x that I want to find. I start with the first guess x0. I calculate fx naught, and then if you look at this equation, I take a tangent at this point, come back to a new guess, which is x1, and then this is my delta u0. This is the increment in the guess that I have achieved through this equation, where I have used, in case of xk, I have used x0, and I have taken this derivative at x equal to x0. So that gave me the tangent, and then finally I got this point. Now I will use this value x1 to xk now is equal to x1, df dx is evaluated at x1, and I get delta u1, which will take me to x2, which is obviously a better estimate. I keep doing this till I reach x star. So this is how it works in 1D. And in multi-dimensions, it is a similar procedure, and this is how we handle it. So now we are looking at a vector, let's say a vector valued function, could be tensor valued as well, vector valued function of a vector x. So we want this to be equal to 0. So this has n functions hidden in it of n variables. So this has a solution which is a vector. So suppose again we have reached the kth iteration of this process, and we want to go to the k plus 1th iteration. To do that, again we linearize f about xk. So we linearize f about xk in the direction of the next iteration, delta uk, which itself is a vector of the same size as xk. So this gives me my new guess, which is the vector xk plus 1. Now, how do we linearize? We have seen this before. To linearize this, we do the multi-dimensional Taylor series up to the first term. So fxk plus the directional derivative of fxk in the direction of delta uk evaluated at x equal to xk, just like in the 1D case. So this quantity that we write as dfxk is actually the directional derivative with respect to xk of f in the direction of delta uk. So this is the quantity that we have to determine. Now, just like in the 1D case, let us set this quantity at xk plus 1 equal to 0, and the new estimate of x is xk plus delta uk, and then to calculate delta uk, what we have to do is we are setting fxk plus the directional derivative of f in the direction of delta uk equal to 0, which means that fxk equal to minus delta xk f of. If we can evaluate this, this is obviously known from the previous iteration because we already know we already know xk, therefore we know fxk as well. So from this equation we will solve for delta uk, and if we can do that, then we will add it to the previous iteration, that is xk, to get xk plus 1. This will continue till delta uk, till xk and xk plus 1 become equal by some measure. So now this quantity we have evaluated before, and we have done a problem some time ago where we showed that for n equations involving n variables of the form fx equal to 0, the directional derivative with respect to x of f in the direction of some vector delta u can be written as k times delta u k. This can be written as k times delta u. Delta u in this case is the kth estimate delta uk, and k is this square matrix. So finally this equation, this entire equation, can be written as k times delta uk equal to minus f at the kth iteration. So this is what we solve. That means we invert k to get delta uk, and invert k and multiply it with f to get delta uk, and then plug it in here in order to get the next estimate. Keep on doing this till, as I said, by some measure, xk and xk plus 1 become uh, indistinguishably close. Okay, so this is how the Newton-Raphson would work for a system of equations, and in this case, this quantity k, which is actually the directional derivative of f in the direction of delta uk, will turn out to be what we will call as the tangent stiffness matrix.